an honor to open the conference. It's also rather daunting. I've not worked directly on effective field theory for some time, and so I could certainly not do justice to modern developments in the field. After I listened to the recording of Steve Weinberg's opening talk in the first conference, I thought it might be good to give a historical talk. And Steve had done such a complete job of discussing the effective chiral theory that I decided to talk about the history of the Heavy-Quark Effective Theory. But I found this more difficult than I expected. I was surprised at how much of this beautiful material I'd forgotten. Well, getting old is interesting. So please bear with me as I try to mine my memory as best I can. I should warn you that this will be a very personal reminiscence. So I've not tried to do a complete catalog of all of the many, many contributions to this field. What I want to share with you is the how I personally experienced the development and came in particular to the velocity superselection rule and the what I think of as the Heavy-Quark effective field theory. First, let me just say a little word about Steve Weinberg's paper and his contributions. His paper on phenomenological Lagrangians at the Schwinger Festschrift is a true masterpiece. I read it at least once a year just for inspiration, and I recommend that everyone do that. I was particularly impressed with his delicate treatment of Schwinger. I was fascinated to learn that it was Schwinger who had suggested that Steve use a nonlinear representation of SU2 cross SU2 long ago. But Steve was very generous in his discussion of Schwinger's source theory. I personally don't think there's much connection. I took Schwinger's course at Harvard when it was a course on source theory, and there just wasn't a lot of effective field theory there. But for Steve, effective theory was a philosophical principle. He wanted to build it from the bottom up. I can just hear him saying, as he did frequently in the talk, the most general possible quantum field theory. I interacted with Steve a lot while he was at Harvard and collaborated with him on a couple of projects. He was one of the few people I know who didn't use examples. He really started from generalities. He liked general principles. He didn't like specific models. One of the great ironies, I think, is that he got his Nobel Prize primarily for a specific model. So while I love the philosophy of effective theory, I'm fundamentally a model builder. I like to build explicit models, explore their structure, think about what they tell us about quantum field theory, and when possible, compare them with data. But I'm usually interested in going top down from a model of physics at higher scales to physics at observable lower energies. So for me, effective field theory is mostly a very convenient tool. Going top down, I'm much less interested than Steve in the most general possible quantum field theory. Top-down effective theory, field theory is not a new idea. One could argue that it goes back to Cauchy and the idea of continuum mechanics in the 19th century. We are all used to teaching our students about how to take the continuum limit and go from a discrete picture at short distances to a continuous picture at long distances. What makes this more interesting in quantum field theory is the need for regularization and logarithmic renormalization in perturbation theory, which blurs the distinction between scale, blurs the division between scales. I think I can say that my own interest in effective theory developed in the early 70s when Shelley Glashow and I were searching for models that could unify SU2 cross U1. We were having fun building models when James Burkane, when BJ, did something rather confusing that turned out to be important for the history of guts. He came up with a numerological relation for the ratio of the E mass to the mu mass. Here it is, ME over MU is 3 alpha over pi log 2. He argued that this is the kind of thing that could come out of a quantum field theory, and that it was right at just about the level one would expect if there were radiative corrections. It's right up to order or alpha squared. In hindsight, this seems absolutely ridiculous. But you have to remember that at this time in 1972, there was no tau lepton, and we weren't quite sure what to think about quarks. For many East Coast physicists at the beginning of the 70s, quarks were still a shorthand for symmetry properties of the still mysterious strong interactions. Now, of course, this situation would change like dreams in the next couple of years. But in early 1972, it didn't seem completely unreasonable to construct models in which the ratio of the electron mass to the muon mass was calculable. At this time, Steve Weinberg was still at MIT, and he got interested in the same problem. So it settled down to an amusing contest between Shelley and me at one end of Massachusetts Avenue in Cambridge, and Steve at the other end, to see who could compute the electron muon mass ratio. And although I think Shelley and I eventually came closer to that goal, Steve made theoretical contributions that were more important to the future of guts. He wrote a paper which described a model of leptons, his second model of leptons, and much less well known than the first. This is a brilliant wrong paper. It did not produce a finite calculable electron mass. He just missed a counter term. Model building was not his forte. Shelley and I solved this technical problem, but the results were not very interesting because, of course, the whole idea was completely nuts. But the really interesting thing about Steve's model, was that it was a kind of proto-gut. The gut-like properties can be seen in a simpler model with only one SU3, with both fermions transforming as threes. And here it is. You put the neutrino and electron and the mu plus in one triplet, and the electron neutrino, the mu minus, and I'm sorry, this should be the muon neutrino, mu minus and E plus in another triplet. And the unlike SU2 cross U1, but like all gut models, this SU3 model has gauge interactions that we haven't seen. In this case, the right-handed interactions, weak interactions involving the top and bottom components of the triplets, and the weird doubly charged W exchange interactions connecting E minus and mu plus, which of course were the interesting things from this point of view, because they gave rise to a diagram that could produce the electron mass from the muon mass. To get rid of them, to get rid of these unwanted interactions, Steve Weinberg invoked what he called super strong symmetry breaking. He imagined that there was an octet of scalar fields with a VEV in the lambda 8 direction, like this, that breaks the SU3 gauge symmetry down to the SU2 cross U1 of the standard model. And it gives a large mass to all of the unwanted gauge bosons, so that the SU2 cross U1 model emerged as an effective quantum field theory below the scale mu U of the expectation value of the phi. Unlike the heavy unobserved fermions in previous models, these super heavy gauge bosons were constrained more by their virtual effects than by direct bounds on production. This was something new at the time. At this point, it goes without saying that Steve was not thinking about what we now call gut scale masses. A few or 10 times the W mass would be plenty to suppress the unwanted interactions to an acceptable level. Nevertheless, at this time, this was a pretty radical concept. You see, we all still thought of the W as very heavy. To invent things that were much heavier still was a bizarre act of genius. But it got me thinking in terms of sequential breaking of gauge symmetries, which divides up the energy scale into regions describing very different physics. And that was the beginning of my interest in effective quantum field theories. Steve did something else in this period that turned out to be very important to my thinking. And that was his discussion of mass-independent renormalization schemes. The idea was to treat masses as coupling constants. This was very appealing to me because it was something I was already doing all the time in symmetry arguments with spirions, treating masses as spirions. Weinberg's paper described other advantages of this procedure. At some level, I knew this already because MS bar subtraction is also mass independent. But like many other physicists at the time, I wasn't quite sure what to make of dimensional regularization. It was great to see how a mass independent scheme could be implemented in a more conventional and familiar cutoff scheme. Anyway, less than 2 years later, after asymptotic freedom and the suggestion of quark confinement, Glashow and I finally decided to try to unify color SU3 along with SU2 cross U1, and it took only one full day. After some general discussions with Shelley in the afternoon, I went home and in one long evening constructed first the SO10 model, and then the SU5 model, and then realized that SU5 would produce proton decay. The next morning, I explained to Shelley the good news about SU5 and the bad news about proton decay. And he explained to me, as he often did, that I was being stupid because proton decay was the way we were going to see unification. But at that point, we were stuck with very large mass scales. There was a lot going on at the time. So it was over 6 months before Quinn and Weinberg and I turned to the question of why the strong interactions are strong in a gut model. We sort of knew the answer. It was obviously coupling constant running, but we didn't have a totally satisfactory way of dealing with it. The problem, as we say in the paper, is to bridge the gap between values of the scale where the large unifying group imposes relations among the gauge couplings, and the ordinary values of the scale where the gauge couplings are measured. What we did, in fact, was an effective field theory calculation. We justified this by an appeal to the Appelquist-Carrizone theorem. Our naive matching of gauge couplings at the gut scale was an appropriate first approximation because the log of the gut scale over the electroweak scale is so large. But this is really not good enough for various reasons. It was clear that what we did was a good first approximation, but it was not obvious how to calculate corrections in a systematic way. And the Appelquist-Carrizone theorem is about matrix elements and not directly about effective theories. The problem was that it was not obvious how to use a practical, or one problem was that it was not obvious how to use a practical mass-independent renormalization scheme like Weinberg's or MS bar, because there's only one counterterm for the coupling constants in the symmetric gut theory. There were absolutely heroic attempts by Goldman and Ross and by Marciano to do the calculation in the physical renormalization scheme, but it was clear that this is not the best way to go about it. The solution, as you all know, is to use matching and running in a tower of effective field theories. I learned this from Steve's beautiful paper, Effective Gauge Theories. Lawrence Hall then turned this into a practical effective field theory calculation. And for me, these two papers delineated what I think of as continuum effective quantum field theory, using a mass-independent renormalization or subtraction scheme, as opposed to Wilsonian effective theory, in which one thought about high momentum modes being integrated out. In retrospect, I realized that I should have paid more attention to my office mate in the late 70s. Before his canonization as the chief prophet of string theory, Ed Witten, with whom I shared an office from 1976 to 1980, did great quantum field theory. He was clearly one of the first people to understand the process of matching and running in quantitative detail. And one can see all of the pieces in his paper on short distance analysis of the weak interactions. But they were not laid out in a systematic way as they were in Weinberg's paper. And it was pretty early, you just didn't get it. So in the early 80s, I tried to put my thoughts about effective field theory down in my monograph on weak interactions. And one of the things I struggled with was the meaning of dimensional regularization. The physical idea of a regularization scheme is that it is a modification of the physics of the theory at short distances that makes the quantum corrections finite and allows us to calculate them. If we modify the physics only at short distances, we expect that all of the effects of the regularization can be absorbed into the parameters of the theory. That is how we chose the parameters in the first place. But in a Feynman graph in which the external momenta are of order mu, Euclidean to avoid embarrassment, dimensional regularization leaves the physics at the scale mu unchanged, but it modifies the physics both at much higher scales and at much lower scales. So my conclusion was that dimensional regularization is really a regularization only for IR convergent graphs, where the changes at lower scales didn't contribute and thus didn't do any harm. Matching and running calculations in effective field theory are okay. But to this day, I get puzzled when IR contributions from dimensionally regularized graphs are taken seriously. In the late 1970s, physical review journals were dominated by non-physics editors. They were nitpicky. They were overly concerned about keeping interesting nomenclature out of the journals. And they were overly egalitarian, bending over backwards to avoid the appearance of favoritism to established researchers. But perhaps most damaging, they were more concerned that papers be not wrong than that they be interesting. The result was that it was easier to get boring papers into these journals than it was to get interesting papers in. And the journals tended to fill up with papers that were perfect illustrations of Cowley's epithet, not even wrong. Many authors got so annoyed that they didn't submit to physical review letters or physical review D. A personal example is my paper with Ian MacArthur, Instantons and the U-Quark mass. I could easily guess where the reviews came from. And though this was certainly not one of my most important papers, I felt that it was interesting and subsequent events showed this to be true. But I got tired of fighting, and so the paper only exists as a preprint. This is not so much of an issue now if authors get annoyed and don't bother to publish, because since 1991, we have had the archive. But back then, it really made it hard to find some interesting works. I must have complained about this publicly, because Elsevier asked me to be the North American editor of Physics Letters B and gave me a free hand to do it right, which I think I did for many years. For example, I sometimes accepted papers immediately if they were obviously interesting. One result of this was that I was very busy. My colleagues often asked, when does Georgi sleep? And the answer was not often enough. But a great advantage was that I got a great view of interesting goings on in North American theoretical physics, because so many of these papers crossed my desk. One disadvantage was that I sometimes didn't pay enough attention to important stuff that got sent to physical review letters instead of PLB, like this one. Here I knew the cast of characters very well. My student Ben Grinstein had done wonderful work on effective field theories, supersymmetry, and CP violation before going off to Caltech. Mark Wise came to Harvard as a junior fellow in 1980, and he had done spectacular work on effective field theory with Fred Gilman at Stanford in 1983. And I just had a marvelous time doing physics with him. It is hard to describe how much fun this was. Suffice it to say that he was a fan of terrible movies. His favorite was Conan the Barbarian. I missed him greatly when he went off to Caltech in 1983. I got to know Nathan Isgur when I first went to Toronto to give a colloquium. I was extremely impressed with the group that Nathan, Gabriel Carl, and others had put together. They were brilliant, mostly brilliantly following up the work that Deruchila and Glashow and I had done on the QCD quark model. But beyond being brilliant, Nathan was just a warm and wonderful person. He knew that his model building was at that stage far from being a first principles calculation. He used to refer to the complicated mess of low energy hadronic physics as brown muck. But focusing on states containing heavy quarks, he hoped to find gems of first principles information about QCD hidden in the brown muck. And they were getting close. If I had studied the paper closely enough, I might have realized that there was something really interesting about the endpoint region in semi-leptonic decays that they focused on, but I missed it. Another serious disadvantage was that I had little time for the rest of the world. And this was a mistake, particularly because there was really interesting physics coming out of the Institute for Theoretical and Experimental Physics in Moscow. That's a nice picture of the main building. This amazing collection of physicists, including Levo Kuhn, Misha Schiffman, Arkady Weinstein, Misha Voloshin, and many others, independently constructed much of the physics of the Standard Model while working under the miserable conditions of the Soviet system. One non-physics story we heard from them was about the stacks of preprints that we used to send to Russia before the archive made paper preprints unnecessary. These were highly prized, not just for the physics, but also for the envelopes, which were of much higher quality than they could get locally. It turned out that if you took one of the old stringy chickens that you could get in Russian stores and baked it inside one of the preprint envelopes, it became much more tender and edible. This was the recipe for what was called preprint chicken. At any rate, I did not pay enough attention to many important papers from ITEP, including these two papers by Schiffman and Voloshin that identified some of the important physics of heavy quark bound states. For the first one, there's a preprint online, so I really had no excuse. They were looking at semi-leptonic B and C decay, focusing on an interesting limit in which the mass difference between B and C quarks is very large, so there's not a symmetry between B and C in the conventional sense, but that the masses are much larger still. And what they realized was that in spite of the large mass difference between B and C, when the initial and final quarks are both at rest in some frame, the brown muck of light quarks and gluons hardly notices anything happening in the transition. So in the limit that the heavy quark masses go to infinity, they are both at rest, and they're both at rest. The matrix element of the weak current is completely calculable. They also did an effective field theory calculation of the matching from the high energy theory to the effective theory below the C quark mass. Shmuel-Nusanov and Wetzel, whom I don't know, also noticed that the matrix element was calculable. But they hid the argument at the end of a paper about other things. But they had the right idea. This is the same argument that and in fact, well, this is basically the same argument that the brown muck doesn't see anything happening. Politzer and Wise, and also Schiffman and Voloshin, considered also transitions between B quarks and C quarks and light quarks. And they found the running, excuse me, they found the running of the relevant heavy to light currents from the heavy quark scale down to low energies. In this region, because the heavy quark, the momentum transfer to the heavy quark is small compared to the quark mass, Politzer and Wise could simplify the form of the heavy quark propagator. Here it is. The Politzer and Wise paper was submitted to Physics Letters, and it was clearly interesting, so I accepted it. But I didn't get as excited about it as I should have, because I didn't understand the generality of their propagator trick. This is actually a key element of the Heavy-Quark Effective Theory, and I should have noticed that right then. But at the end of 1989 and the beginning of 1990, 3 interesting papers that explored this further crossed my desk for Physics Letters B. This one may have been nuclear physics, but I saw it in Physics Letters B. The Eichmann and Hill paper, and a month later, Grinstein constructed an effective field theory for the heavy quark bound state in its rest frame, translating the Isgur-Wise propagator trick into a more explicit effective field theory language. Grinstein also discusses the 1 over M expansion in diagrams with an arbitrary number of loops. So one of the reasons that I made a big deal about Physics Letters is that the next 2 papers, when they were submitted to PLB, made me sit up and take notice. The Isgur Wise paper, like the Eichmann Hill and Grinstein papers, is about the static quark approximation. But they mention the magic word that gets my juices flowing: symmetry. More than just symmetries, they were talking about new symmetries of QCD. For me, this was a bombshell. I have loved symmetries in quantum mechanics since I first encountered the quantization of angular momentum in beginning quantum mechanics. And most of my work throughout my career has revolved around symmetry. And here were Isgur and Wise telling me that they had found new symmetries that I had never seen. In fact, there were 2. The spin symmetries were not really a surprise. I had thought about them in the context of quark-bound states in the early 1970s. Isgur and Wise were just using them much more cleverly in a new context and much more reliably in the new context. But the flavor symmetries were a real shock. Their explanation made it very obvious, however, in the bound state of a heavy quark and light antiquark, or pair of quarks at rest, the light QCD part of the bound state, Isgur's brown muck of hadron physics, just sees a static source of color electric field, and the brown muck doesn't care whether the color field is being produced by a B or a C, to leading order in the inverse quark masses. So if you remove the trivial kinematic dependence of the heavy quark mass, there is a symmetry between the brown muck and the B and D mesons. With this symmetry, the normalization of the B to C matrix element that previous authors had noticed physically emerged simply as, and obviously, because the currents were the Noether currents associated with these new symmetries. Once I understood this, it was pretty obvious that this symmetry will emerge as an accidental symmetry of an effective field theory of the static heavy quarks. But before I had a chance to do anything about this, their second paper arrived on my desk. This is about symmetries again, but this was unlike any typical symmetry argument I'd ever seen. What was going on with this universal function? I was puzzled and fascinated. Although their argument is not stated entirely in terms of symmetry, their physical picture is very clear. Different velocities of the heavy quark are completely independent. And that was the key. It suggested the velocity superselection rule. And for me, that was the aha moment, and the rest was pretty easy. This was one of those papers that almost wrote itself once I had the idea. Everything followed simply from the velocity selection rule. The advantages were obvious. In the heavy quark effective theory, below the heavy quark scales, there is a separate term in the Lagrangian for each quark and heavy quark velocity and anti-quark velocity. And the brown muck of the low energy QCD couples to each of them, but to leading order in 1/m, it's all the same. There's no communication between the different velocities. So the velocity the velocity superselection rule is implemented. Lorentz invariance is incorporated explicitly, but in a weird way. The Lorentz transformation shuffles the velocities around, but in a perfectly covariant way, so it's very clear how to implement Lorentz invariance in matrix elements. The most exciting part from my point of view was that there are an infinite number of heavy quark spin and flavor symmetries, one for each velocity of quark or anti-quark. And they all arise automatically. They emerge just because the Lagrangian fractures into independent descriptions of the physics at each velocity. In Weinberg's terminology, there are an infinite number of accidental symmetries in this low energy theory. So this formalism that I developed incorporated all of the different applications of the heavy quark limit that had happened to that point into a single picture. The huge symmetry also allows for much simpler derivations of the result. And this is the beginning of the paper, where I note that what I was doing was just trying to understand these brilliant papers on the static limit. But the idea here was that it made it simple enough for me to understand because of all of these symmetries. It actually took a little time for the full power of the infinite symmetry in heavy quark effective theory to sink in. For a few months, I continued to see papers that justified their results with complicated arguments that were completely unnecessary because the results followed directly and simply from the symmetries. But I knew that the tide had turned when I received a paper for physics letters B from Mark and his collaborators with a sheepish note saying something like, "This paper is not earth-shattering, but it has one great virtue. It uses the heavy quark symmetries." My favorite immediate application of heavy quark effective theory is this little paper by Ben and Mark and my then current student, Adam Falk. Adam's interesting. He is a terrific physicist and a wonderful teacher, but he was such a good teacher that he went on to become president of Williams College and is now president of the Alfred P. Sloan Foundation. At any rate, this paper uses all of the pieces of the heavy quark effective theory. Oops. That's out of order. These three diagrams are from the paper. I had to recreate them for this talk to make them show up better. They describe the leading QCD effects on the heavy quark current in three regions. The high energy region above the or at the matching scale between the high energy theory and the heavy quark, the first of the heavy quark theories. The intermediate region, if you're looking at a B to C decay, where one of the quarks is heavy and the other is light. And finally, the low energy region, where both quarks are light. And The double lines are the fixed velocity propagators from the Heavy-Quark Effective Theory. In the low energy theory, we found a velocity-dependent anomalous dimension, which gave a logarithmically enhanced contribution to the Isgur Wise function. And it's the dominant contribution to the form factor of the B meson state for very large masses. You can also see the advantages of writing a paper with the editor of the journal. We could get in stuff that would never be allowed in a PhysRev journal. Take a look at the footnote. Here we've named the Isgur Wise function after Isgur and Wise. And the footnote is, if you can't read the fine print, one of the authors, MBW, objected to this name, but the rest of us ganged up and overpowered him. But the good news is that our name stuck, and it's a fitting tribute to Nathan and Mark for their brilliant work on heavy quarks. So let me close by showing you a little drawing that was done many years ago by Michael Peskin. It shows me wading through a swamp of hadronic brown muck, no doubt searching for those symmetries that I love so much. So in closing, let me just say that my modest contribution to the Heavy-Quark Effective Theory is one of my favorite accomplishments, not because I think it's the most important, but because it involved one of those really striking aha moments that we all cherish. And because it gave me an excuse to celebrate the Isgur Wise symmetry found by these two special friends. But there's absolutely no question that my most important contribution to effective quantum field theory, both before and after Heavy-Quark Effective Theory, was encouraging a generation of extraordinary graduate students to approach quantum field theory from this point of view. My students and grand students and great-grand students and so on have contributed to this field in ways that I could not even imagine. So thanks for listening and have a wonderful conference.